Okay, today in class we learned about domain restrictions on functions. Our objectives for this lesson are to determine if there needs to be a restriction on the domain of a given function in context, and also to identify solutions of linear and exponential equations. Restricted domains, these are values of the domain that need to either be included or excluded to make the function reasonable. For example, if the function h of n gives the number of person-hours it takes to assemble n engines in a factory, then the positive integers would be an appropriate domain for the function. What this means is that the positive integers, those would include like 1, 2, 3, 4, 5, they would be appropriate for the person-hours it would take to assemble engines. We cannot have a negative amount of engines, so we would say that our positive integers would reflect the engines that we are trying to produce. So in our first example, it says to graph the function using the intercepts, then determine if there needs to be a restriction on the domain. Now we're going to review graphing a function using the intercepts, and the first thing that might be helpful is if you take the equation or the function that is given to us, the f of w equals 2w, and we write it as a linear equation. To write it as a linear equation, we replace the f of w with a y. And then we go and we take, if you would prefer, instead of using a w, we could instead use an x. And then we go to solve this using our x and our y intercepts. If you can remember that when we are trying to find the x-intercept, we have to decide what value is 0. When we're looking for the x-intercept, the y value is 0. However, when you're looking for the y-intercept, the x value is 0. And we're going to use that information and plug that into our equation y equals 2x. So to start with the y-intercept, we're going to replace the y value with 0 and then solve this equation for x. To solve this equation, we divide by 2, and 0 divided by anything gives us 0. So we have x equals 0, and I'm going to replace that in my ordered pair here. We do the same thing when we're looking for the y-intercept, except that you're going to replace the x value because it tells you right here that the x is 0. So in our equation, we'll replace that x with the 0 here and then solve it. 2 times 0 is 0, and this is where we have a little bit of a problem. If we go to graph these two values, the x-intercept and the y-intercept, they are on the same point on our graph. So when that happens, you're going to have to create a table of values. So over here, I'll create a table of values. And when I say create a table of values, I'm probably going to choose like a negative, and we've already done 0 twice, so we don't need to do it again, and I'll do 1. So when I do this, remember I'm going to take that negative 1 and I'm going to put it into the equation wherever the x is. So my equation is y equals 2x, and I'm going to replace this x with negative 1. When I replace that with negative 1, I multiply it by 2, and I get a negative 2 for the y value. We'll do the same thing for this 1, and we'll put it into that x value. So 2 times 1 is 2, so y is 2. And then we have enough values that we can actually graph this. So my first ordered pair from my table says that I have to go back 1, down 2. My second one says I have to go over 1, up 2. And then I have enough information to create a line. Once I have this line, I'm going to go back to the original equation and see what it says. It says that the length f of w of a rectangle is twice the width w and can be represented by the function f of w equals 2w. So really what we're talking about is how a width of a rectangle compares to the length of a rectangle. On our graph, right here we run into some problems with our context. This says that I can have a width of -1 and that gives me a length of -2. We know that in real world rectangles, we cannot have a width of a -1, we cannot have a length of a -2. So when this talks about the domain, remember that domain refers to your x values. So when I come up here, I have to say that x cannot be negative, because if it's negative, the width does not exist. In fact, we want to say that it's not even 0, because if it's 0, you don't have a rectangle, you'll have just a segment. And so I'm going to go ahead and I'll write it up here in this space. For the domain, we're going to say x such that x has to be greater than 0. Now, because we actually talked about w, you could replace this x here and this x here with a w. But while you're solving these here, I don't mind if you use x, because we always talk about how x refers to your domain. But if you want to use it according to our context here with the w, then that would be great as well. So again, here we have another problem. It's just another example to give you a better idea. This talks about a swimming pool and how much it would cost per hour for people swimming at the pool if you were going to rent it. It says it's given by the function f of p equals 50 plus 2p. If you want to do what we did on the last one and actually replace the f of p with y equals 50 plus 2 and replace the p with an x, then you can do that, unless you want to deal with this in function notation. So on the last one, we want to do the same thing where we look for the x-intercept and the y-intercept. I'll start with the x-intercept. The x-intercept is when your y value is 0. So we're going to take this value, plug it into the equation wherever y is, and then solve this. So I put 0 in place of the y equals 50 plus 2x. From here, we can subtract 50 from both sides, and we get negative 50. These 50s subtract out, equal 2x. Okay, then you'll divide by 2 to both sides, and that will give you a value for x. These 2 divide out, and negative 50 divided by 2 is negative 25. So we can put that back in our ordered pair up here for the x-intercept. We'll do the same idea for the y-intercept. The y-intercept is when our x value is 0. So we're going to put 0 in and find out what we get out. So we go into that equation, y equals 50 plus 2x, and we replace the x with 0. Now this 2 times 0 is 0, so we don't need to put it in there, and what you get left for y is just 50. This is good. On the last one we got 0, 0 on both of those. And here we get 2 different distinct points. The only problem is that when you go to your graph to graph this, you're going to have to change the scale, because if you want to go by ones, we'll never get to negative 25 or to 50. So I'm going to suggest that my x values, let's go by 5s, and our y values, let's go by 10. So I'm going to go back 5, 10, 15, 20, 25, up 0 for my x-intercept. For my y-intercept I have to go up 50, 5, or over 0, up 50, 5, 10, 15, 20, well I went by 10s, 10, 20, 30, 40, 50. And then I have the line. Now, again, you have to go back to what you started with and talk about how is this graph related to my context. Now, according to my graph, if I say I go back even 25, that would say that I have negative 25 people. Now, we all know that we can't have negative 25 people. You have to have positive people for you to even be charged a flat fee, and then $2 per person. So all of our x values on the graph right here would give us a situation that doesn't actually occur in real life. So from there we're going to talk about what would we use for our domain. In this case it's P, and I'm going to write it up at the top because I've got some room there. So our domain restriction, we're going to say P such that P what? Now I said p because that's our x value. If you'd like to put x there instead, that would be fine. But we know that p has to be greater than, for us to even rent the pool, you got to be bigger than 0. You could even say greater than or equal to 1 if you wanted to be more specific. And the other way that we could also say this, instead of using our set notation, you could say that p has to be positive integers. And that would eliminate any decimals where this one includes those decimals. So to be better and more specific, we would say p has to be positive integers. Our last example, example 2, says to determine if the given point is a solution to each equation or inequality. So it wants us to take this value that it gives us, this negative 3, 5, and put it into the equation. And I'll start with that right now. So I'm going to replace the y right here with the 5. 5 is greater than negative 1/3. Then I'm going to replace the x with the x that's given, which is negative 3. And then I'm going to solve this. So I have 5 is greater than negative 1/3 times negative 3 is positive 1. 1 plus 2 is 3. Now I'm going to read this. Is 5 greater than 3? Yes, it is. It's a true statement. So what that means, if I were to graph this equation, it might look something like this. And because it's an inequality, y is greater than, so we would shade above. And it says that any point that's either on this line or above the line would be considered a solution. And this point that we have here is above that line, so it's considered a solution. We go to the last example for B. We're going to do the same thing. This equation that's given to us is actually exponential. You realize that because the x right there is an exponent. So because of that exponent, we're going to go ahead and solve that. Remember, it will end up looking like a curve if we were to graph it. This negative 4 says that it would approach on the axis. It would approach on the axis, negative 4 right here. Anyway, we're going to go ahead and put that in. We're going to replace the y with a 7, so it'll read 7 equals 3 to the first. We're replacing that x with the 1 minus 4 and then solving it. 3 to the first is 3 minus 4 is negative 1. We can see that 7 does not equal negative 1, and so the point 17 is not on our curve, and so this would be a no. It is not a solution. And that should help you with the rest of your examples. Good luck, and I'll see you when you return.